두 번째 발표는 텍사스 A&M 임종희 교수님 발표인데 그 사정상 동영상을 보내주셨습니다. 그래서 이번 시간은 같이 임종희 교수님께서 보내주신 발표 영상을 함께 신청하는 시간으로 갖겠습니다.
먼저 코로나 바이러스로 모두가 힘든 시기에 학술대회에 참여해 주신 여러분과 어려운 여건 속에서 학술대회 진행을 맡고 있는 사무국 관계자 여러분들께 감사의 말씀을 드립니다. 그리고 실시간으로 발표를 진행해야 하나 개인 사정으로 인해 녹화된 영상으로 발표 내용을 전해드리게 된 점 양해 부탁드립니다. 발표는 영문 학술 용어 및 표현이 친숙한 관계로 부족하지만 영어로 진행하도록 하겠습니다. The title of the presentation is Locomotor Coordination, Visual Perception, and Head Stability During Running. Human locomotion has been described as self-optimizing to produce stable coordinated patterns. Central pattern generator within the spinal cord serves to modulate basic underlying locomotor patterns by integrating afferent feedback from proprioceptors of the muscles and joints with higher level inputs from the brain. Then efferent stimulation is transmitted through motor neurons to individual muscle groups for the effective movements. As such, sensory motor control loop for human locomotion serves to modulate basic underlying locomotor patterns. However, there are another important cyclic and rhythmic relationship exists between the perceptual and locomotor systems. In 1979, Gibson stated that we must perceive in order to move, but we must also move in order to perceive. This foundational concept of perception and action coupling emphasizes that continuous cyclic relationship between information from the body and environment and the necessary adjustment of the body is critical for the stable pattern of the behavior to occur. So these optimized patterns help individuals to identify and evaluate visual information in order to select safe and efficient path of navigation. Head is an important part of the body. All important sensory organs, visual, auditory, and vestibular systems are located. So during walking or running, the clear visual image about the surroundings could be achieved by stabilizing the head. The successful navigation of the visual field will be more challenging, especially during the running than walking, and also when environments are more variable and dynamic. However, we have a lack of knowledge about the specific mechanisms about how head and visual field stability are regulated during locomotion. One of the major threats that hinder the head stability during running is the impact shock. Impact shock from the foot-ground collision is transmitted throughout the body and all the way up to the head. So without the proper attenuation and regulation of this impact shock, runners will be faced with difficulty in stabilizing the head and therefore the visual field. Ground reaction force or acceleration profile have been used to assess the impact and loading characteristics during running. In general, impact shock can be regulated in two different ways. As you see in this video, vertical ground reaction force during running shows two distinctive peaks, one at the heel strike and the second at the late portion of the stance pace. However, this pattern can be changed by simply wearing the shoes, which is a good example of passive impact shock attenuation. Another way to regulate the impact shock is to actively adjust the footfall patterns. As you see in the last video, forefoot running style significantly changed ground reaction force characteristics. So runners can regulate the impact shock by the combination of passive and active mechanisms. Studies in the literature demonstrate that individuals appear to organize their kinematic patterns to regulate the amount of shock transmitted to the head, and this contributes to the stabilization of the visual field. Increased shock attenuation has been observed in response to changes in gait parameters, such as higher speeds, lower stride frequency, and longer stride length. The knee joint has consistently been reported to play an important role in shock attenuation, specifically through greater knee flexions. As you see in the figure, impact peak at the leg increased or decreased as a function of stride frequency, but acceleration at the head was relatively constant across the stride frequency ranges. So it was speculated that the constant head acceleration may serve to stabilize the visual field. In summary, the stabilization of the head in response to altered stride parameters and running speed has been well established. However, the inverse, how the body adapts and attenuates impact shocks to different head stability or perceptual demand, is less clear. So dual purposes of the study were to identify how individuals adapt their running kinematics and the resultant alterations in shock transmission in response to increases in head stability requirements, and also to identify changes in segment joint coordination and coordination variability in running with increasing head stability requirements. For the study, 12 recreational runners were recruited. Their average running speed was about 3.1 meters per second. All participants were free of injury and neurophysiological disorders. Informed consent and questionnaire about health and physical activity readiness were provided. 8 motion capture cameras were operated at 120 Hz, and 2 triaxial wireless accelerometers were mounted to the tibia and head, and time synchronized with the camera system. Kinematic data of the head were imported, and the intersection of the head gaze vector on the screen was calculated in real time. A white dot representing the intersection point was projected on the screen. A projector was mounted on the ceiling, and a screen was located at 2-meter distance from the treadmill. A dot line at the head of the runner in the figure represents the imaginary head gaze vector toward the screen. On the screen, only the intersection point, not the trace of it, was displayed during running. This is a demonstration of head motion tracking. A 6 degree of freedom object was created and attached on the head using crown. Intersection point of the extended virtual head vector on the target plane was calculated and displayed on the screen in real time. Participants ran at their preferred speed and stride frequency while performing visual tasks. Visual task was to keep the head gaze within the box projected on the screen. 7 different box sizes from 21 to 3 degrees of visual angle were used in the study. Once head gaze was stabilized within the box, 30 seconds of data collection were started, and 15 strides occurred in the middle were used for the analysis. For the visual task, we systemically decreased the virtual boundary box size from 21 to 3 degrees of visual angle. So the instruction was to run at their preferred speed while maintaining the head gaze point inside the box. So this is a trial demo. As you can see here, a dot moving in the box indicates the motion of the head gaze point during running. Once gaze point is stabilized within the box, 30 seconds of data were collected. For the analysis, path of the head gaze on the screen was reconstructed, and head kinematics, including 95 ellipse area, path length, and average velocity of the path, and the range of the gaze point were calculated. Stride parameters and joint kinematics were also analyzed. Power spectrum density of the head and tibial acceleration were determined. Gain or attenuation of impact shock transmission was determined from a transfer function. This is a reconstructed head gaze from representative participants. As expected, head motion decreased as head stability demand increased. significant effect of visual condition for time head gaze stayed in the box was observed. Particularly, shorter time in box for 6 and 3 degrees of visual angle was observed than all other visual angles. TBI and head acceleration profiles in time and frequency domain show the significant main effects of visual condition during active portion of stance. Smaller visual angles resulted in smaller peak amplitude and integrated power of the head accelerations. However, during the impact portion of stance, no main effects for visual condition were observed for all acceleration profiles of both the tibia and head. These findings indicate active adjustment of the head acceleration occurred in late stance. A main effect of visual condition was also observed in the mean transfer function between tibia and head accelerations. Significantly greater reduction in acceleration amplitude were observed for smaller visual angles during the active portion of the stance. This figure shows mean percent change for the key dependent measures from visual angle 21 conditions. Runners were able to meet the visual task demands without changing their running kinematics until visual angle 15 conditions. But gradual changes started to appear from visual angle 12 condition. The most difficult condition, which is 3 degrees of visual angle, resulted in 32% reduction in head gaze motion. To achieve this reduced head motions, stride frequency increased about 8%. Hip flexion and impact was also increased about 14%. And 56 less extended hip and 50% more flexed knee joint angles at toe off were also observed. 8% increase of stride frequency was associated with decreased stride time, but no changes in stance time were observed. So throughout the visual task, constant stance time were maintained. 14% increase of hip flexion at impact was associated with increased hip heel distance in anterior posterior direction, but no differences in knee heel distance in anterior posterior direction were observed. Increases in heel landing position relative to the knee have been associated with elevated ground reaction force magnitudes and loading rates during impacts. But it's been known that the greater sagittal plane hip heel distance, but not knee heel distance, is associated with larger braking forces. So the observed lower limb joint configurations were regulated to maintain constant impact loadings. Lastly, smaller hip extension and greater knee flexion occurred at toe off are likely contributed to reducing the vertical, trunk, and pelvic oscillations. However, these changes might have negative impacts on the running economy because it reduces aerial time and forward propulsive force during late stance pace. As head stability demand increased, shock attenuation was not different in early stance, but was observed greater during the later portion of the stance. This suggests that increased head stabilization occurs through the active compensatory mechanisms in the 4 to 8 Hertz ranges. In the previous literature, Pojo reported that mean amplitude of head angular displacement in running was about 13.5 degrees. So this study is in support of this finding and demonstrate active regulation of running kinematics is necessary to stabilize the head in smaller than 12 degrees of visual angles. Adaptive changes in lower limb kinematics and stride parameters appear to reflect changes in voluntary control that occur without increased impact loadings. Coordination analysis provides information about spatial and temporal organization of the movement and its flexibility and change in motor strategies. So coordination and coordination variability analysis were performed for head and trunk segments, hip and knee joints, and knee and ankle joints. For the coordination analysis, coupling angles at each individual point of the stance space were calculated using modified vector coding techniques and circular statistics. 4 different coordination patterns were determined from the coupling angles. In-pace motion represents segments of the interest rotating the same direction. Anti-pace motion represents segments of the interest rotating in opposite directions. Distal and proximal paces represents one segment rotating while the other segment is relatively stationary. For the coordination variability measures, one-dimensional spatial parameter mapping statistical analysis was performed. This statistical techniques allows us to detect differences in coordination variability waveform between the visual conditions. In the example in this slide, dark gray region above the threshold dot line on the figure right represent the specific time in stance space where the effects of walking speed is observed on the variable. Significant changes in coordination patterns were observed in 3 main sites in the body. As you see in the figure, increased in-pace and decreased anti-pace sagittal plane coordination were exhibited for the hip-knee, knee-ankle joint coordination. These lower extremity coordination patterns facilitate reducing the vertical range of motion of the body. Also, there was a significant increase of anti-pace coordination and head-leading coordination for the transverse plane head-trunk coordination. This was considered as fine-tuning of the rotational control in the trunk and head. Overall, these changes in coordination patterns indicate that a joint and segment-specific function may exist for the stabilization of the head motion during running. For the coordination variability analysis outcomes, coupling angle variability in the left column and spatial parameter mapping result in the right column were presented. An increase in coordination variability in both the upper body and lower extremity couplings appeared to occur in late stance. And this may serve to enhance the flexibility of the system in line with increasing visual task demands. Overall, the results provide evidence that coordinative adaptations to increasing head stability demands occur throughout the entire body. And these changes occur to facilitate the more independent control of the head relative to the trunk and contribute to the reduction of range of motion in vertical directions. The systemic reduction of head gaze motion during visual tasks suggests that there is a perceptual underpinning to the regulation of the transfer shock through the kinematic chain. This study provides some evidence that individuals can tune running mechanics in order to stabilize the head orientation under increasing visual task demands. Mechanisms by which individuals stabilize the head with increased visual task difficulty predominantly occur in late stance, suggesting these are adaptive, active adjustment. The observed changes in coordination patterns indicate that joint and segment-specific function may exist for the stabilization of the head motion during running. These are the references used for the presentations. 이상으로 발표를 마치도록 하겠습니다. 발표와 관련하여 질문이 있으시거나 추가적인 내용이 필요하시면 제 이메일이나 역학회 사무국을 통해 문의해 주시면 답해 드리도록 하겠습니다. 감사합니다.
큰 박수 한번 치겠습니다. 네, 마지막 임종희 교수님께서 제 마지막 멘트를 해주셨는데 혹시 질문 있으신 분들은 임종희 교수님께 직접 메일 드려도 되고 아니면 역학회 사무국으로 질문 주셔도 될 것 같습니다. 그러면 예. 오늘 첫 번째 날 두 번째 세션은 이것으로 마치고 마이크를 사무총장님께 넘기도록 하겠습니다. 수고하셨습니다.